Hello, and welcome to this session on configuration management in a service mesh world. My name is Martez Reed. I'm a training solutions engineer at Puppet. I can be found on LinkedIn as well as Twitter. So for this particular session, the agenda that we're going to walk through is what is a service mesh agent deployment, service mesh agent bootstrapping, as well as implementing micro-segmentation with service mesh. All right, so we'll get right into what is a service mesh. A service mesh is a dedicated infrastructure layer for facilitating service-to-service communications between microservices, according to Wikipedia. And so that's kind of a mouthful of what it actually does. And so we've actually got a number of things that it actually does and why someone would want a service mesh. So service discovery is the first thing that people often think of when they think of a service mesh, as well as traffic management, observability, mutual TLS, along with fault injection. So the picture to the right includes projects from the CNCF landscape in the particular service mesh category. And so we'll actually kind of walk through some of those, but the ones we'll really focus on will be Kuma, which is a project created by Kong, HashiCorp Console, as well as talk a little bit about Istio. So Linkerd is also one of the other popular service meshes. But the thing with Linkerd is that it is solely focused on Kubernetes and not to be really leveraged in a hybrid manner. And so there is no virtual machine agent for Linkerd. So as we talked about, one of the first things that people think about when they mention service mesh is service discovery. And so service discovery is the process of automatically detecting devices and services on a network. And so this sounds very familiar to DNS or name resolution. And so one would say, what's the difference between this and name resolution? And so let's walk through this example and see. And so the first thing that actually happens is a service registers itself with effectively a DNS server, but it's part of the service discovery. And so it's not your normal DNS server. It's something like a HashiCorp Console or a Kuma or a Linkerd. And what it does is the service registers itself based upon an agent. And so that's why we see agent registration. And so what it does is it says, hey, I'm at this particular IP address. And so the value of this in comparison to normal DNS is that what this enables us to do is leverage workloads that are particularly ephemeral. And so if the database is in a container and it comes and goes on sort of a whim, and it may not necessarily be at that particular same IP address the next time that it comes up, or in the case of a web server or an application server. So what this does is similar to DNS. So now there's the workload that wants to know where the database is at. And so it says, hey, where's the database? And in this case, our DNS server, which is our service discovery server, responds back and says, hey, it's at this particular IP address, and sends it back. And then what the application then does is it reaches out to the database because it now knows where the database is at. The other big advantage of service discovery is health checks. And since it's leveraging an agent to help facilitate the service discovery, what the agent can do is also leverage health checks, or basically checking the health of the service, and so that we don't send requests to a service that has failed. So it provides the robustness as well as the dynamic nature of name resolution for an environment with containers and workloads that come and go. The next big reason people use service mesh is traffic management. And this is very similar to load balancing in sort of the traditional VM environment, where we have load balancers, and load balancers send traffic to a particular service or a node on the back end. And so in the case of like Istio and Console and Linkerd and even Kuma, they have various options for traffic management. And some of them may include the examples shown here, like weighted load balancing. So this is a common example that is shown, also known as traffic splitting. And so it's particularly relevant when people start leveraging microservices to enable them to sort of gracefully roll out a new version of a service to where, like in the example, we have version 1 of the service receiving 80% of the traffic, and then version 2 receives 20% of the traffic. And then what we can do as part of this is continually decrease the amount of traffic that goes to version 1 of the service and increase the amount of traffic that goes to version 2 of the service based upon what we're seeing from logs and seeing if version 2 of the service is responding as we expect it to. Additionally, there are things like least request load balancing, as well as round robin load balancing. So these give us all of these options in terms of how we manipulate traffic within our service mesh. The next big advantage is what's known as observability. And so this is really just a collection of data about our applications and what's going on in terms of microservices in our environment or in our service mesh in this particular case. So one of the things is traffic metrics, as well as distributed tracing and traffic logs. And so on the right of the slide, there are a number of projects that are involved in observability. And so one of them is Prometheus for grabbing data from the environment. You also have things like Jaeger and Open Tracing for distributed tracing to be able to allow applications to have that data being presented to the service mesh without the actual instrumentation of applications. So typically when you leverage tracing, you need to instrument applications. And so that means there needs to be a change in the code of the application in order to take advantage of that. But the advantage of a service mesh is that you're able to do that without actually instrumenting an application, because the service mesh has visibility into the network. And so it can see the request from service to service and provide that visibility. A couple of others are Zipkin as well as Grafana to be able to bubble up information. The next one is particularly interesting. It's mutual TLS. There's been multiple iterations of forms of mutual TLS in computer networking. The really interesting thing about mutual TLS from an application perspective that we're leveraging now with a service mesh is that we're able to transparently do this, and so that the application doesn't have to really know about what's going on in terms of the data encryption. So that's where we get the end-to-end encryption. So there's no change to the actual application to enable encryption between one service and another, which removes a lot of overhead in terms of needing to code that into your services or in this case, like a database for the connection piece. And so the other advantage it provides is identity-based authorization. And so this is particularly interesting as we can leverage the mutual TLS. What underpins it is X509 certificates. And so what we can do is leverage those X509 certificates to handle authorization between services and be able to allow or deny traffic based upon identity. One of the others is advantages of service mesh is fault injection. So what do we mean by fault injection? And so this allows us to apply certain scenarios from, let's say, a network perspective to our application to test resiliency. And so one example that we'll actually go through here is network delay. And so the first service wants to talk to the second service. And so it sends the request. And then what we're actually doing is adding a delay into the response. And so we added a 6-second delay into the response. So what that allows us to do is test the resiliency of the service that is submitting the request, and in terms of knowing what to do if there's been a delay in the response and be able to handle that appropriately. A number of other options depending upon the service mesh is HTTP aborts, which allows an updated response to be replied back to the actual original request. So an example would be returning a 500 HTTP error code in response to a request. And so this response is actually coming from the service mesh and not the actual backend service itself. And so this allows us to do some testing of resiliency and how our application responds in failure scenarios without actually modifying the application itself, but simply leveraging the capabilities of the service mesh to manipulate things. And the last one, as an example, is bandwidth limiting. And so this is limiting the response bandwidth. And so if you submit a request and then on the response, the bandwidth is limited. And so if it's like a very large response, then it may take a while. And so it adds that effectively that delay while simply just leveraging bandwidth limitation. And so we've talked through some of the advantages of a service mesh, and some of the challenges that organizations will begin to face is the fact that they're starting to leverage the service mesh in their Kubernetes environment. And then ultimately, they're going to get to a point where they need to integrate those applications in the Kubernetes environment to applications running on virtual machines or on bare metal, or what people typically refer to as now legacy workloads. And so this is really, how can we integrate Kubernetes workloads that have got all the advantages of the service mesh capabilities being harnessed, and then integrate that with our legacy workloads in a meaningful manner. So we'll take a look at that. So the first thing we'll take a look at is agent deployment. And so in a service mesh, typically the architecture is two primary components: a control plane and a data plane. The control plane holds the data plane configuration. And so what that means is the data plane interacts with the control plane to get information about what the configuration of the data plane should be. And the data plane is what actually directly interacts with the flow of data. And so in this particular case, it's things like the request from service to service. And so the data plane actually handles the sort of the nuts and the bolts of it. So we'll delve a little bit deeper into some of the aspects of service mesh and how it actually works. So one of the big things is sidecars in the case of Kubernetes. And so a sidecar is an additional container added to a Kubernetes pod, specifically for the purpose of providing functionality that supports other containers in the pod. And so what does that even really mean? And so in the example of the GIF, we have the motorcycle, and the dog is in what's known as a sidecar. And so the actual functionality is provided by the motorcycle. The sidecar provides additional functionality in terms of enabling an additional passenger to be able to ride along, but it by itself does not provide the core functionality. And so this is very similar, based upon its name, to sidecars and Kubernetes. And so common examples would be log shippers. And so needing to ship logs from your application that runs in the pod and ship it to something like an Elastic or a Splunk. And so what that sidecar container does is it just handles the role of grabbing data from the primary container and then shipping that log data to the logging platform. Similar with monitoring agents, and very similar with service mesh agents. And so what it does is provides the capability we want from a data plane perspective, running in tandem with the actual primary workload. And so from a pod perspective, you have at least two containers running in the pod. One is the primary application, and then one is the service mesh agent. And typically, it's just simply referred to as a proxy. And so deployment in Kubernetes of sidecars is typically handled via what's known as injection. So sidecar injection. So what Kubernetes is able to do is immediately inject a sidecar proxy or container into the pod when the particular pod starts up. And so I've included an example of Kuma Service Mesh. And so it's this one line that's added to the Kubernetes configuration that simply enables every pod, let's say in the cluster or in a particular namespace, to be deployed automatically next to your application. And so this is unbelievably easy in terms of actually just getting this running. And so adding that proxy to the application to actually handle the traffic as part of our service mesh makes it so easy. So we look at Kubernetes, and obviously there's a lot of architecture decisions and configuration that's been sort of embedded or baked into the platform to make things like this very easy. So the challenge is, how do we do that on something like a virtual machine or bare metal? So obviously those that have been around configuration management for a while understand that this is the perfect place for a tool like Puppet, is to kind of help facilitate that service mesh agent injection into our virtual machines in a manner similar to Kubernetes. And so that allows us to be able to ensure that there is a proxy running next to our application effectively on our virtual machine. Now, it's not a single one-line configuration file or configuration, but it hopefully gets to a point where you're simply declaring a class, like let's say Kuma or console, to be applied to all of your virtual machines. And at that point, the virtual machine then gets the service mesh agent. And so we've got to the point where we've got the agent running on our virtual machine in the case of virtual machines, and then it's been dynamically injected into the pod in the case of Kubernetes. And so now there's a second step that needs to take place, which is the agent bootstrapping. Those that are obviously familiar with Puppet know that there is the actual installation of the agent, and then there's a bootstrap process or additional actions or operations that need to be taken in order to facilitate the connection between the agent as well as the server in the case of Puppet. So we'll take a look at that and how that works with a service mesh. So in this particular case, we've got the proxy installed. It's been injected next to our application. And so what happens next is, in the case of a service mesh, leveraging mutual TLS requires an identity. And in this particular case, and in most cases with service mesh, it's leveraging an X509 certificate to provide the identity for the individual workload. And so we kind of have this chicken and egg scenario, like with the Puppet Enterprise Bootstrap, Puppet Enterprise Agent bootstrapping process, in which we have the whole certificate auto signing process that needs to happen after the agent's been installed. And so we have a similar conundrum with the service mesh agent. And so we need to get the certificate, which is generated by the service mesh control plane, to the actual workload, in this particular case, right next to the workload in the case of the proxy. And so what happens in the case of Kubernetes is that there is a Kubernetes service account that is leveraged for identity, an initial identity, to the service mesh control plane. And then it can do that verification to say, oh, yes, you're this particular workload. Great. Now, here is your X509 certificate that matches your identity, which will be leveraged by the mutual TLS piece, as well as workload policies to provide the capability of and the advantages of mutual TLS. And so some of the challenge is this process is very easy on Kubernetes because it's got the built-in service account capability and functionality that's sort of very much tailored to this sort of workflow. But the challenge is, how do we do that in a virtual machine or bare metal world? And so once again, same sort of scenario. And so how do we get the token? In this particular case, there's a JOT token that is needed, that is presented from the proxy to the Kuma mesh in this particular example. And so we want to present that and then get back an X509 certificate. The challenge is, where does the proxy get that initial token from? In the particular case of the Kubernetes example, it leveraged a service account, which is provided to every container, or in this case, every pod in a Kubernetes environment. And so in the case of a virtual machine, the token isn't readily available on the node. And so how do we get that and present it to our service mesh control plane in order to be able to get our X509 certificate for identity? So that's where configuration management comes into play once again. And so in this particular example, we're using Puppet Bolt to provide some of that orchestration capability. And so in the example of Kuma, Puppet Bolt reaches out to the Kuma control plane and says, I would like a data plane agent token. And so this is that JOT token that we talked about. And so it says, I need the token for this particular virtual machine. Can I have the token? Kuma then returns the token for that particular virtual machine. Bolt then sends it over to the virtual machine, likely laying it down into a file that the service mesh agent can pick up and ultimately present to the service control plane. So in this particular example, it's generate a token, write the token to a file on the virtual machine, and then restart the data plane agent service on the virtual machine to help bootstrap that process. And then once that's done, the virtual machine now has some way to provide a form of identity, initial identity to the control plane, and then ultimately get back that X509 certificate as part of the capabilities. And so the next piece that we'll talk about is micro-segmentation as part of a service mesh. And so in a service mesh, one of the big advantages is that mutual TLS that we talked about. What that provides us is the ability to do workload specific segmentation, in this case, based upon identity. And the identity is that X509 certificate that each of the workloads got when they bootstrap themselves as part of the service mesh. And so in this particular example, we're taking the sort of very traditional 3-tier application, a web server, an application server, a database server. And so for those that have worked with microsegmentation in some form, whether it's been VMware's NSX in a VMware environment, or even those that have worked in public cloud environments of understanding the construct of security groups. Security groups in most cloud environments, from a best practice perspective, is to leverage sort of the idea of microsegmentation, which is only grant applications or workloads the network access that it needs, nothing more than what it needs. And so in this particular example, it's the web server is permitted to talk to the application server because that's what we expect normal communication or traffic to be. The application server can talk to the database server. And so that's the flow of the traffic. And then obviously there's also leveraging established connections to provide that response. But where it really gets interesting from a micro-segmentation standpoint is you start to block traffic. And so the assumption is that my web server should never really talk directly to my database server, and my database server shouldn't be trying to talk to my web server. And so we're not going to allow that traffic. In a similar fashion, the database server likely isn't going to actually initiate a connection to my application server. It's the other way around. The application server is going to initiate traffic to the database server, and I'm going to allow that established connection to provide the response. And I don't expect the database to reach out to the application server. Similarly, I don't expect the application server to reach out to the web server. And so I've blocked that communication as part of my micro-segmentation to ensure that, let's say, a rogue process on my web server doesn't somehow get directly to the database and have that sort of unfettered access. And so this is the advantage of micro-segmentation, is it helps prevent lateral movement in a network if the environment is breached. This helps prevent, or at least slow down, movement of a hacker or malicious individual from just moving about the network as they please. And so the other piece we talked about was a little bit about workload policy. The real advantage of the mutual TLS capability or feature of service mesh is that we can leverage identity-based policies to define which services can and cannot talk to one another. And so how that works is that our particular application sits next to a proxy, which is provided by the service mesh agent. And similarly to normal proxies that we would think of in sort of other walks of the IT space, this controls traffic to and from other resources. And so in this particular case, we might have a Node.js application that needs to talk to a Mongo database. And so in the case of a service mesh, we would leverage proxies to actually handle that communication between our application as well as our database. And that gives us that identity-based authorization or policy capability. And so what this looks like is the Node application talks to the proxy that sits next to it to say, I would like to send this communication to the database service. And so the proxy then takes it, sends the request over to the proxy for the database. But what's happened in this particular example, it may be an actual database that doesn't belong, let's say, to this microservice. Maybe it's another microservices database. And what we've done is we've leveraged X509 certificates for our identity to say, this particular application should not be able to talk to the database for this other application. And we're going to leverage the identity associated with the X509 certificate to perform that blocking action. And so similarly, as we talked before with microsegmentation, this allows us to really start to lock down which applications and which workloads can talk to one another and which ones can't. And so in the case of service mesh, what we're doing this from is a service level or an application level. And so we're providing that segmentation between which service can and cannot talk to one another. So in this example, we've got service 1 talking to service 2, but that traffic is denied. Similarly, service 2 can't talk to service 3. Service 3 can't talk to service 4. And so we've also allowed service 1 to talk to service 3, service 2 to talk to service 4. What this allows us to start to see is we can start to provide that isolation at a service level. And so we're only allowing services that should be able to communicate to one another, which in an ideal world is how it should be. And what service mesh has enabled is this paradigm at a much simpler to implement capability without needing to directly modify applications. And so one thing that the service level segmentation does not do is that it does not actually isolate traffic from the actual pod in the case of Kubernetes. So in that case, the traffic that's destined for a service that is defined in the service mesh is controlled, but traffic outside of that isn't controlled. And so an example would be, let's say I want to talk to www.google from one of the containers in my pod, or I want to talk to some database that isn't part of the service mesh, then there's that unfettered access once again by default, unless I leverage a construct known as Kubernetes network policy, or something similar to it from a third-party vendor. But what this does is allows us to isolate workloads at the Kubernetes pod level. So in addition to that service-based identity, microsegmentation, we then layer on Kubernetes network policy to provide an additional layer of security to dictate what can and cannot come in and out of the pod. And so by default in Kubernetes, all pods are allowed to talk to one another. So there's often policies where I may lock it down to a namespace where only pods in a particular Kubernetes namespace can talk to one another, or I may get even more granular to the point of where I want to explicitly define which pods can and cannot talk to one another to ensure we're reducing the possibility for lateral network movement in this case, potentially a rogue pod. Let's say you roll out some piece of software you found on the internet, and the container has something malicious in it. And so now, without tight segmentation, it's got access into your Kubernetes cluster to potentially just roam and roam and roam, which isn't ideal. And so with network policy for Kubernetes, you can leverage ingress filtering, so traffic coming into the pod, as well as egress filtering to determine which traffic is allowed to exit the pod. From a selector basis, we can leverage particular pods in terms of how we define our rules. We can leverage, as I said, namespace, and then we can also leverage IP address-based filtering. In the case of, let's say, we're talking to an on-prem environment or something that we want, that's something that's very static in nature in terms of the IP address. And so there's the construct of Kubernetes network policy in Kubernetes, but if I've extended my service mesh into virtual machines or bare metal, how can I leverage a similar construct to provide that capability? And the one way I would say it is host level firewalls. It's a construct that's been around for years and years and years, but one of the traditional challenges to implementing good microsegmentation via host level firewalls, in my opinion, has been just simply being willing to adopt the idea of microsegmentation and really get granular in terms of what access is and is not allowed. And so I think this is the perfect time to be able to leverage that, especially with something like Puppet, where you can easily define what's allowed to talk to one another and what's not allowed. And so we're kind of continuing to implement these layers of security and taking advantage of the constructs and the concepts that service mesh has sort of unlocked, and taking that a step further to provide additional isolation. And so being able to leverage Puppet provides a very similar construct in terms of isolation as the Kubernetes network policy does. So being able to leverage those in tandem, I think, is very ideal. So the last thing is kind of a summary, wrap up what we talked about. There's a lot of things and a lot of concepts, but ultimately it's being able to extend your service mesh out to virtual machines is a very much worthwhile endeavor. And Puppet or another Puppet allows us to do that pretty easily in terms of automating that process. And so talked about service mesh and what it is and what it does. We've automated the deployment of service mesh agents, leveraging Puppet. We understand that on Kubernetes, it leverages Sidecar injection. Puppet, we can leverage the traditional automation of install the package, configure the service, configure the configuration files, all those things like that. We also looked at orchestrating the bootstrapping process of understanding that there's some identity pieces that we need to grab from the service mesh as part of an orchestrated sort of dance. And then lastly, we took a look at augmenting service mesh microsegmentation with host firewalls and Puppet. And so it's, as I said, really just taking it that next step and continuing to further those good concepts and paradigms of microsegmentation throughout the environment. Thank you for joining the session, and feel free to post any questions.